Welcome to this walkthrough of LeetCode problem number 513, find bottom left tree value. In this session, we will explore the problem statement, break it down step by step, and discuss a key approach to solve it. Let's dive in. In this problem, we are working with a binary tree, and our goal is to find the value of the bottom leftmost node. The bottom leftmost node is defined as the leftmost node in the last row of the tree. The input for this problem is the root of the binary tree, and the output should be an integer representing the value of this specific node. To better understand the problem, let's look at some examples. Here's the first tree. We have a root node with a value of 2, and it has 2 children, 1 on the left and 3 on the right. For this example, the last row of the tree contains the nodes 1 and 3. Since we are tasked with finding the leftmost value in the last row, the correct answer is 1. Now, consider another example where the tree is larger. The root node has a value of 1, with 2 children, 2 on the left and 3 on the right. The left child, 2, has its own left child with a value of 4. On the right subtree of the root, the node with value 3 has 2 children, 5 on the left and 6 on the right. Finally, there is a node with value 7, which is the left child of node 5. In this second example, the last row of the tree consists of the nodes 4, 7, and 6. Among these, the leftmost node is 7, so the output for this tree is 7. Now, let's examine a third example where the tree is left skewed. Here, the root node has a value of 1, its left child has a value of 2, and the chain continues with a left child of 3. In this case, the tree has only one path, and the bottom leftmost node is at the end of this chain. Since the last node in this tree is 3, the output is 3. For constraints, the number of nodes in the tree can range from 1 to 10,000, and the value of each node is within the range of -2 to the power of 31 to 2 to the power of 31 1. Let's also consider some edge cases. If the tree consists of only one node, that node is both the root and the bottom leftmost node. In a left-skewed tree, where all nodes only have left children, the bottom leftmost node is simply the last node in the chain. For a right-skewed tree, even though all nodes are aligned to the right, the bottom leftmost node is still the last node in the single row. Finally, in a balanced binary tree, we need to ensure that the leftmost node in the last level of the tree is correctly identified and returned. To solve the problem of finding the bottom left value in a binary tree, we evaluated a few approaches. The first approach we considered was a recursive depth-first search, or DFS. The intuition here is to traverse the tree deeply, path by path, while keeping track of the depth at each step. With this information, we can update the bottom left value whenever we reach a new maximum depth. DFS is particularly useful because it allows us to fully explore each path in the tree systematically. By maintaining the depth during traversal, we can confidently identify the deepest level and its leftmost node. However, this approach comes with some trade-offs. Since recursion is used, the call stack requires extra memory proportional to the height of the tree, which is O(h). Despite this, the recursive DFS guarantees that all nodes are visited, making it a sound choice with a time complexity of O(n) and a space complexity of O(h). The second approach we considered is iterative breadth-first search, or BFS. Here, the intuition is to use a queue to traverse the tree level by level, also known as level order traversal. At each level, we can track the first node encountered, which is the leftmost node for that level. By processing all levels, the first node of the last level will give us the bottom left value. BFS has some key advantages. It naturally traverses the tree in level order, which aligns perfectly with identifying the leftmost node of the deepest level. Unlike DFS, there's no need to manually track depth. The trade-offs include memory usage, as BFS requires queue storage proportional to the maximum width of the tree, O(w). However, this method ensures that all nodes are processed level by level, making it efficient and reliable. BFS, like DFS, has a time complexity of O(n), but its space complexity depends on the tree's width. After evaluating both approaches, we chose the iterative BFS strategy for this problem. One of the main reasons is its efficiency. BFS processes nodes level by level, which makes it straightforward to identify the bottom leftmost value without requiring additional bookkeeping or recursive calls. This avoids the risk of stack overflow in very deep trees. Another reason is the clarity of the implementation. The BFS approach is simple and intuitive, as we only need to iterate through levels and record the first node at each level. Finally, BFS is robust. It handles all kinds of tree structures gracefully, whether they are balanced, imbalanced, or have varying depths. The key insight that solidified our decision was realizing that BFS inherently traverses the tree level by level, and the first node encountered at each level is always the leftmost node. This made the solution both efficient and elegant. When comparing DFS and BFS, there are some notable trade-offs. DFS, while effective, requires manual tracking of depth and relies on recursion. This introduces the risk of stack overflow in very deep trees and adds some complexity to implementation. BFS, in contrast, avoids these issues by using an iterative approach with a queue. In terms of memory usage, DFS uses O(h) space for the call stack, where h is the height of the tree. BFS uses O(w) space for the queue, where w is the maximum width of the tree. For balanced trees, height h is approximately log n, while width w can approach n/2, meaning BFS can be more memory intensive for wide trees. Both approaches share the same O(n) time complexity, but BFS stands out for its ease of reasoning and alignment with the problem requirements. Ultimately, we selected BFS for its simplicity, robustness, and direct alignment with the goal of efficiently finding the bottom left value while maintaining clean and concise code. To solve the problem of finding the bottom left value in a binary tree, we first need to understand the goal. Given a tree, like the one illustrated, the objective is to locate the leftmost node in the last row. In the example tree, the bottommost row contains only the node with value 7, making it the leftmost node at that level. To achieve this, we use a recursive depth-first search, or DFS, approach. This method ensures we traverse the entire tree, keeping track of the maximum depth encountered and updating the leftmost value whenever we reach a new depth. Now, let's break this down step by step to understand how the algorithm works. We begin by initializing two key variables. First, max_depth, which tracks the deepest level encountered in the tree. This is initialized to -1 to ensure that the top level, which is at depth 0, is considered. Second, bottom_left, which stores the value of the bottom left node. This starts as none since we haven't traversed the tree yet. Next, we define our recursive DFS function. This function takes two parameters, the current node and the current depth. The base case is straightforward. If the node is null, we exit the function, as there's nothing more to traverse. If the current depth exceeds max_depth, it means we've reached a new level of the tree. In this case, we update both max_depth and bottom_left to reflect the new depth and the value of the leftmost node at this level. Finally, to ensure we prioritize the leftmost node at each depth, we always traverse the left child first, followed by the right child, incrementing the depth by 1 with each recursive call. Once the traversal is complete, bottom_left will hold the value of the desired node. The key to this algorithm lies in a few insights. First, by traversing the left subtree before the right in our DFS, we guarantee that the first node encountered at each depth is always the leftmost. Second, the max_depth variable acts as a checkpoint, allowing updates to bottom_left only when a new depth is reached. This ensures that we don't overwrite the value unnecessarily. The recursive nature of DFS makes it efficient for this task, as it breaks the problem into smaller subproblems, focusing on one subtree at a time. In terms of data structures, the algorithm only requires a few variables, max_depth to track the deepest level, bottom_left to store the leftmost value, and the call stack, which is managed inherently by the recursion. The input tree is represented as nodes with val, left, and right properties. When it comes to complexity, the time complexity is O(n), where n is the total number of nodes, since each node is visited exactly once. The space complexity is O(h), where h is the height of the tree, as this corresponds to the maximum depth of the recursion stack. Now let's translate the algorithm into Python code. We begin by defining the findBottomLeft value method within a solution class. Inside, we define our recursive DFS function, which takes the current node and depth as parameters. To keep track of max_depth and bottom_left, we use the non-local keyword to modify these variables within the function. The base case checks if the node is null, in which case the function simply returns. If the current depth exceeds the max_depth, we update both max_depth and bottom_left to reflect the new depth and the value of the leftmost node. The traversal prioritizes the left child by calling DFS on the left node first, followed by the right node, incrementing the depth with each call. Before starting the DFS, we initialize max_depth to -1 and bottom_left to none. The DFS is then invoked with the root node in depth 0. Once the traversal is complete, the value stored in bottom_left is returned as the result. This implementation is concise, efficient, and directly follows the algorithm we've outlined. This algorithm handles a variety of edge cases effectively. For a single node tree, the node itself is the bottom left value by default. In a left-skewed tree, where all nodes are aligned to the left, the algorithm correctly identifies the last node in the sequence. Similarly, in a right-skewed tree, where all nodes are aligned to the right, the algorithm still prioritizes the leftmost node at the maximum depth, even though the left subtree may be null. For a balanced tree, the algorithm ensures that the leftmost node at the deepest level is chosen, regardless of the structure. While breadth-first search, or BFS, could also solve this problem, DFS is preferred here as it avoids the overhead of storing all nodes at each level. By traversing the left side first, DFS guarantees correctness without requiring additional checks. This makes it a space-efficient and elegant solution to the problem. This implementation solves LeetCode problem number 513, find bottom left tree value using a level order traversal, breadth-first search, BFS, approach. The goal is to find the leftmost node value in the bottommost row of a binary tree. We start by importing deque from the collections module, which is used to efficiently implement the BFS queue. Inside the find bottom left value method, we initiate a queue with the root node and declare bottom_left to store the leftmost value at the current level. The main logic resides in the while loop, which iterates as long as there are nodes in the queue. At the start of each level, we assign the value of the queue's first node, q0.val, to bottom_left. This ensures that the first node processed at every level is recorded as the leftmost node. We then iterate through all nodes at the current level, using for and range, len, q, and remove them from the queue using popleft. For each node, its left child, if it exists, is added to the queue first, followed by its right child. This order ensures that nodes are processed left to right at each level. Once the loop completes, the bottom_left variable holds the value of the leftmost node in the bottommost row of the tree. This value is then returned as the result. This solution efficiently handles all edge cases, including trees with only one node, null children, or highly unbalanced structures. It operates in O(n) time complexity, where n is the number of nodes, as each node is visited exactly once. The space complexity is O(w), where w is the maximum width of the tree, corresponding to the size of the queue at its largest level. Here, we start by defining the treenode class, which represents each node in the binary tree. Each node has an integer value, as well as left and right child pointers. Then, in the solution class, we implement the method findBottomLeftValue, which will help us find the leftmost value in the last row of the tree. To do this, we use a level order traversal, also known as breadth-first search, by leveraging a queue. We initialize the queue with the root node and set the bottom left variable to the value of the root as a starting point. The while loop begins the traversal, and it continues as long as there are nodes in the queue. Before diving into each level, we update the bottom left variable to the value of the first node in the queue, because this node represents the leftmost node at the current level. Next, we determine the number of nodes at the current level using queue.size, and then process each node at that level using a for loop. Inside the loop, we remove the front node from the queue and examine its children. If the current node has a left child, we add it to the queue. Similarly, if it has a right child, we add that to the queue as well. This ensures that we traverse all nodes level by level, from left to right. Once the queue is empty, the traversal is complete, and the bottom left variable holds the value of the leftmost node in the last row. Finally, we return bottom left as the result of the method. This approach efficiently finds the desired value using a time complexity of O(n), where n is the number of nodes in the tree, since each node is processed exactly once. Here, we start with a simple binary tree. The root node has a value of 2, with 2 children, 1 on the left and 3 on the right. To determine the bottom left value, we initialize a queue with the root node and set the bottom_left variable to none. At the first level, the queue contains only the root node, which means the leftmost value at this level is 2. We process the root node by dequeuing it, then enqueue its left child, 1, and its right child, 3. The queue now contains nodes 1 and 3. Moving to the second level, we update the bottom_left value to 1, as it is the leftmost node at this level. We process node 1 by dequeuing it, noting that it has no children to enqueue. Similarly, we process node 3, which also has no children. At this point, the queue is empty, so the algorithm terminates and returns the bottom_left value, which is 1. In the next example, we work with a deeper binary tree. The root node has a value of 1, with 2 children, 2 on the left and 3 on the right. Node 2 has a left child, 4, while node 3 has 2 children, 5 on the left and 6 on the right. Initially, we enqueue the root node and set bottom_left to none. On the first level, the queue contains only the root node, so we set bottom_left to 1. After processing the root, we enqueue its left child, 2, and its right child, 3. The queue now contains nodes 2 and 3. On the second level, we update bottom_left to 2, the leftmost value at this level. We process node 2 by dequeuing it and enqueuing its left child, 4. Then, we process node 3, enqueuing its children, 5 and 6. The queue is now updated to contain nodes 4, 5, and 6. On the third level, the queue contains nodes 4, 5, and 6. The leftmost value at this level is 4, so we update bottom_left to 4. Processing begins with node 4, which is dequeued, and since it has no children, nothing is enqueued. Next, node 5 is dequeued, and similarly, no children are added to the queue. Finally, node 6 is processed in the same manner. At this point, the queue is empty, and the algorithm concludes by returning the bottom_left value, which is 4. Now, consider an unbalanced tree, where each node only has a left child. The root node has a value of 1, with its left child being 2, and node 2's left child being 3. We start the process by enqueuing the root node and setting bottom_left to none. On the first level, the queue contains just the root node, so bottom_left is updated to 1. After processing the root, we enqueue its left child, 2. The queue now contains only node 2. On the second level, the leftmost value is 2, so bottom_left is updated to 2. We process node 2 by dequeuing it and enqueuing its left child, 3. The queue is now updated to contain just node 3. On the third level, the leftmost value is 3, and we update bottom_left accordingly. Processing continues with node 3, which is dequeued. Since it has no children, nothing is added to the queue. At this stage, the queue becomes empty. With no more nodes to process, the algorithm completes and returns the bottom_left value, which is 3. In all these examples, the approach systematically traverses each level of the binary tree while updating the bottom_left value to the leftmost node found at that level. By the time the queue is empty, the algorithm guarantees that the bottom_left variable holds the correct answer. This efficient level order traversal ensures we can handle trees of varying depths and structures while maintaining clarity and simplicity in the implementation. The time complexity of the find bottom left value function is O(n), where n represents the total number of nodes in the binary tree. This is because the algorithm performs a level order traversal using a breadth-first search, or BFS. Each node in the tree is visited exactly once during the traversal, and for every node, its left and right children are added to the queue if they exist. This results in n iterations of the loop, one for each node in the tree. Additionally, the queue operations, such as appending a node to the queue or removing one with popleft, are performed in constant time, O(1). Since these enqueue and dequeue operations are performed exactly n times across all levels of the tree, the total time complexity remains linear, or O(n). This ensures that the algorithm efficiently processes all nodes without any redundant operations. The space complexity of the find bottom left value function is O(w), where W represents the maximum width of the binary tree. The width is defined as the maximum number of nodes present at any single level in the tree. During the BFS traversal, the algorithm uses a queue to store nodes at the current level, and the size of the queue peaks at the level with the most nodes. For a complete binary tree, this maximum width is approximately n/2, leading to a worst-case space complexity of O(n). Beyond the queue, the algorithm only uses a constant amount of additional memory for variables like bottom_left and loop counters, which means the auxiliary space is O(1). Therefore, the overall space complexity is dominated by the queue size, making it O(w). In the worst case of a complete binary tree, where W is approximately n/2, the space complexity simplifies to O(n). In terms of best, average, and worst-case scenarios, the function behaves as follows. In the best case, where the tree consists of a single node, n equals 1, and both the time and space complexities are O(1). For an average case, such as a balanced binary tree with n nodes, the time complexity is O(n), since every node is visited once, while the space complexity is O log n, which corresponds to the height of the tree. In the worst case, such as a complete binary tree or a tree with maximum width, the time complexity remains O(n), and the space complexity rises to O(n), because the width of the tree is approximately n/2. Comparing this to a brute force approach, which might use a depth-first search to calculate the tree's height and then perform another traversal to find the bottom left value, the time complexity would also be O(n), but with additional overhead for the second traversal. The BFS approach, by contrast, is more efficient and straightforward, as it directly identifies the bottom left value in a single traversal. Mathematically, this is justified because for a complete binary tree, the number of nodes at the last level is roughly n/2, dominating the space usage. Similarly, as every node is processed once, the operations scale linearly with n, confirming the time complexity is O(n). When solving this problem, there are some common mistakes to watch out for. First, if you're using a recursive depth-first search and a global variable to track the maximum depth, forgetting to reset this variable at the start of a new test case can cause incorrect results. This happens because the value from a previous test case might interfere with the current one. Next, it's important to remember that the problem asks for the leftmost node at the bottom level. Traversing the tree in the wrong order, such as visiting the right child before the left, can lead to selecting the wrong node. Finally, when using breadth-first search, always check for null nodes. Assuming all nodes are non-null can result in runtime errors, especially in edge cases like single-node trees or trees with empty subtrees. These are critical points to address for a robust solution. Another common pitfall is inefficient traversal. For example, some solutions use extra data structures like lists to store all nodes at each depth during BFS. This unnecessarily increases space complexity because you're only required to track the leftmost node at the bottom level. Additionally, in recursive DFS, mishandling the base case can cause issues. For instance, stopping recursion too early or not properly identifying leaf nodes can lead to incomplete traversal, which disrupts depth tracking. From an interview perspective, it's essential to clarify assumptions, like whether the tree is guaranteed to have at least one node. If not, explicitly handle the edge case of an empty tree. Also, be ready to explain why you chose DFS or BFS. DFS is often preferred for depth tracking due to its intuitive nature, but BFS can be more efficient for level-order traversal. Finally, interviewers appreciate solutions that optimize space usage, so emphasize how your approach minimizes it. Discussing edge cases like single-node trees, highly unbalanced trees, and trees with duplicate values can also demonstrate thoroughness. This problem connects to several related topics worth exploring. For example, LeetCode 104 focuses on finding the maximum depth of a binary tree, while LeetCode 199 examines the binary tree's right-side view. Problems like LeetCode 112, which deals with path sums, and LeetCode 987, which involves vertical order traversal, are also relevant. In terms of alternative approaches, an iterative BFS is a solid option. This method uses a queue to traverse the tree level by level, tracking the first node at each level. While it's often space-efficient in balanced trees, it may consume more space when dealing with wide trees. Another approach is modified DFS, where you use a recursive function to track depth and value, updating the result whenever a deeper level is encountered. While simpler to implement, this method may struggle with recursion limits in very deep trees. Lastly, a two-pass approach involves determining the maximum depth in the first pass and locating the leftmost node at that depth in the second. Although easy to implement, this method is less efficient due to multiple traversals. Each of these methods has its trade-offs, so choosing the right one depends on the specific constraints of the problem. Great job! To recap, we solved the problem using a recursive depth-first search approach and reviewed its complexities. Remember, mastering tree traversal techniques is essential for tackling similar problems. Thanks for watching, and see you in the next video. That's the end of this tutorial. I hope you found this explanation helpful for understanding the solution to this LeetCode problem. If you enjoyed this content, please consider subscribing to the channel for more coding tutorials and solutions. Feel free to leave a like if this video helped you, and don't hesitate to comment with any questions you might have. Thanks for watching, and happy coding!